Okay, well, hello everyone. Welcome to another week of the GBO Science Lunch Talk series. Today we have a graduate student from the University of Pennsylvania working with Professor Mark Devlin, Jack Orlowski-Scherer. And today he'll be talking to us about his work studying galaxy clusters. So if you have questions during the talk, please feel free to speak up, or you can write them in the chat. And when you're ready, take it away, Jack.
Sure. Thanks for the introduction, Jesse. So like they said, I'm going to be talking about the MaDCoWS mass richness scaling relation. So we'll start with this picture of the universe, which I'm sure people have seen before, but it's good to go back over. So this is sort of our timeline of the universe in the lambda CDM model. All the way on the left here, we have the origins of the universe. We have the Big Bang, and shortly thereafter, there's probably a period of inflation, and that inflation mechanism has some sort of quantum fluctuations in it, and those quantum fluctuations seed over and under densities in the primordial plasma. That those over and under densities in the primordial plasma are captured when recombination occurs. Well, not captured, but the pattern is captured when recombination occurs, and that pattern is emitted as the light of the CMB. So that's what you have here, labeled afterglow light pattern. And then for a long time, there's pretty much nothing, just gas, and that gas is slowly going from those very small over and under densities that were seeded by inflation and collapsing under the influence of gravity and pressure to form the first structure, which are stars that form about 400 million years after the Big Bang. And then those stars coalesce into galaxies, and the galaxies coalesce into clusters. And so as we go forward in time, we have larger and larger structure being formed. So we start with, nothing, microscopic, very, very, very small over and under densities. And then as time goes on, under the influence of gravity, you get bigger and bigger structure. And sort of a key component of this is that the model that you pick to describe your cosmology ends up affecting how fast that structure forms. So what we've got on the right here is just some dark matter simulation. So you've got a cube and you've got all your dark matter particles in it. And it's pretty close to uniform at the beginning, but it's, sorry. Pretty close to uniform, but it's been seeded with some over and under densities. And then as time goes forward, as we wind the clock forward, they form larger and larger structures until towards the present day, you have these big clusters and the filaments between them. And the rate at which this occurs is dependent upon your model of cosmology. So the parameters that you pick, the dark matter abundance, the so on and so forth, all affect how fast this matter accumulates. So in particular, the amount of large scale structure that you see as a function of the size of that structure and of the time of the universe is a strong probe of evolution. So at the most basic level, your lambda CDM model sets a maximum scale for a cluster at a given time in the universe. So if you take your model, you look at a redshift of say 0.5, you'll say, oh, there's a maximum cluster mass. There's a maximum size for a cluster that could possibly have formed in the amount of time prior to this. But you can also look at, that's the most basic thing you can do, but you can also ask, okay, how many clusters of a certain mass do I see at a certain redshift? And does that statistically exceed the number of clusters at that mass and redshift that I expect from theory? So here's an individual cluster that is probing cosmology. So this is El Gordo, which is an absolutely enormous cluster at fairly high redshift. And what we're seeing here, which is getting towards the meat of my talk, is how El Gordo is actually detected. So we have 4 separate detections here. On the top panel, which are very similar, are an optical and an IR image of El Gordo. And so in these images, El Gordo appears as an overabundance of galaxies, so a spatial overabundance of galaxies. In the bottom left, we have an X-ray picture of El Gordo. So this is essentially the X-ray emission from hot gas in the cluster. And you can see clearly the emission there. And then on the bottom right, you have the Signal-Zeldovich signature of the cluster. And I'll go through the effect in a little bit, but essentially the idea is what we're seeing here is a frequency shifting of the photons from the CMB as they pass through the cluster due to inverse Compton scattering of those photons off of gas in the cluster. So great, this is a nice sort of multi-image picture of El Gordo. And this sort of leads to the question, so how do you actually select, how do you actually detect these clusters? And these are the three primary ways: X-ray, SC, and optical. So that's all great, but if you want to really understand your population, if you really want to understand your abundance counts, if you really want to do precision cosmology, you need to understand the selection functions of these various.
What'd you say?
Sorry?
Yeah, I know, but there's a.
I don't think that's meant for me, so I'll continue. You have to understand the selection functions of the various types of surveys. And then you also have to be able to calibrate both the redshift, which we know how to do reasonably well. You basically just go look at galaxies that you think are associated with the clusters and you pull off redshifts from those. So that's pretty straightforward. And you have to be able to calibrate the mass of the cluster. And that's more difficult. And that's basically what we're talking about in this talk is, given a cluster that you detected in the optical or IR, how do you figure out how much it weighs? Yeah, so we're mostly gonna, and the way we're gonna do that is by correlating it with SC signals. So that's why the circle is popping up to tell you it's about optical and SC. So like I said, we'll use the SC signals to calibrate the mass, but the SC signal itself isn't actually a probe of the mass. If you just had SC surveys and you looked at the sky, you wouldn't be able to tell how massive the clusters were. But you can get around that because you can calibrate them with X-ray surveys. So the X-ray signal that you observe does directly probe the mass of the galaxies. And so if you have a number of the mass of the clusters. So if you have a number of clusters that you've detected in both the X-ray and in the SC, you can build a scaling relation where you have, the mass on one axis, and you have this Y twiddle is the centralized Compton Y parameter, which is a measure of the strength of the SC signal, on another axis, and you can just sort of calibrate this scaling relation. And now anytime you make a measurement of the SC signal of a cluster, you can use this scaling relation to figure out what the mass of that cluster is in a statistical sense. So obviously there's some sort of intrinsic scatter about this line because we don't expect these two things to be exactly one-to-one in the sense that they're astrophysical processes that will probably cause deviations from a perfect relation. But as long as you're looking at enough clusters and this, this scatter is pretty narrow, you'll do good enough. So now the question is, how do we do this with an optical survey? So the problem with doing a SC calibration of the masses is that E rho zeta's results notwithstanding, which aren't public yet, their X-ray surveys are generally somewhat limited in the sky coverage that they have. So what you can do instead is you can have an SC survey from a CMB instrument, which does have quite a lot of sky coverage. And you can use the masses that the SC inferred masses or the SC masses to calibrate the mass relation for the optically detected clusters. Whew, that's a lot. Okay, so the idea here is if you observe a cluster in the IR, you don't get an intrinsic measure of its mass, but you can count the number of galaxies that you associate with it, and this is called the richness. And you would expect naively that the mass should scale with the richness. The more galaxies I see that are in a cluster, probably the more it weighs in general. And so this work on the right here is essentially saying, well, what if I go to a number of cluster locations that I've identified in an optical or IR survey, and I just say, you know, what do I think the SZ mass is? What do I think the mass is for a cluster given the SZ signal at that location? And you plot them all, and you can see it's a little bit messier than our previous graph, but you can draw lines through it. So this is two different, the blue and gray here are two different projects that both did that, one including Mustang, which was on GBO, obviously. And so, you know, you can fit a relation to that and it works well, but you'll notice this is an extremely limited subsample. And so the challenge here is to extend this mass richness scaling to a full cluster catalog. One thing to note is that this definition of richness is not standardized across optical and IR surveys. Each optical and IR survey has their own definition of richness. And so you need to do this calibration separately every time, for every survey that you have that has a cluster catalog. So this was done for the MaDCoWS cluster survey, which is an IR cluster survey that I'll cover in detail in a second. And they did a preliminary mass richness relation. That's these points here in gray. They used about 20 points. And they got sort of a preliminary mass richness scaling relation. And basically what we're doing is just saying, well, let's extend that to all the clusters in MaDCoWS. Right, that's what that bullet point says. So just a quick overview of the optical and IR surveys. So this is WISE, the telescope that actually carried out the MaDCoWS surveys. MaDCoWS stands for the Massive and Distant Clusters of WISE. So there's WISE. Like I said earlier, they don't have an intrinsic measure of the cluster mass. So you need to do this mass richness scaling relation. And a couple things to note here is that the detection of these are based on spatial overdensities. Really got to call now? No. They're based on spatial galaxy overdensities. And then, so they use WISE to identify spatial overdensities of galaxies. And then they have follow-up that identifies the clusters associated with, the galaxies associated with that cluster. But you have to be a little careful here because you can have what I've called interlopers, which are essentially just line of sight coincidences of galaxies. That aren't really members of the clusters, but happen to be along your line of sight to the cluster, which can increase the richness, but obviously aren't actually contributing to the mass, and so they can screw you up. So this is what the survey actually looks like. All these gray points are detected clusters. The blue areas, well, they just have a different follow-up. The sort of defining feature of the MaDCoWS survey is that it's a high redshift survey. So all these clusters are between a redshift of 0.7 and 1.5. And so the sort of draw here is, you know, the further out that your cluster abundance function is a function both of the mass of the cluster and of the redshift. So if you really want to constrain the cluster abundance function, you need to find clusters at all sorts of redshifts. And so this is, you know, one of the largest high Z catalogs. I think it's the largest IR selected high Z cluster catalog out there. And so just some sort of more statistics. So there's about 2,800 clusters in the catalog. 1,600 of those are within the ACT footprint, so ones that we could conceivably detect. Interestingly, we find only 96 co-detections. Meaning we find only 96 clusters that we identify with an ACT analog that are spatially co-located with the detected ACT cluster. Part of that is because these are much lower mass in general than the ACT clusters. The average ACT cluster is something like nearly 3 × 10⁻14 solar masses, and these are about 1.6. This estimate, by the way, comes from the preliminary mass richness scaling relation in Gonzalez. And that preliminary estimate is in good agreement with a CMB lensing estimate of the mass that Maccow put out this year, which found a mass of about 1.4. So pretty big error bars on both of those. So yeah, they're in good agreement. So quickly going over the SC effect. So as I mentioned previously, the SC effect is an effect wherein CMB photons are inverse Compton scattered off of electrons in the gas of a cluster as they pass through that cluster, and that imparts a special spectral distortion to the CMB. So the one of the nice features is that it's Z independent. There's no variation of the strength of the signal with redshift. So in principle, you can see clusters out to arbitrarily high redshifts. Although the mass of clusters tends to drop as you go to higher redshift, so you will still see less, but there's no direct Z dependence. The distortion strength scales with the mass. As I said, you need to calibrate this against X-ray surveys. The real big trade-off of this sort of survey is that you have relatively low resolution, and that'll come up in a little bit. So most CMB surveys have resolutions of only about 1 arc minute, which is really poor compared to optical, obviously, and X-ray as well. And just of note here, this is the actual spectral shape of the SC effect. Look at the solid lines, the dashed lines are the KSC effect, which we're not considering in this work. You can see that there's a decrement at about 150 and at 90 gigahertz, which are two primary CMB observation channels. And then there's the null is at approximately 220 gigahertz, which is also a CMB observation channel. And then above that, it's an enhancement of the signal. So the actual CMB instrument involved here is ACT. So it's the Atacama Cosmology Telescope. It's a 6-meter off-axis Gregorian telescope. It has a 3-degree field of view. It currently observes at 90, 150, and 220 gigahertz, although only the 90 and 150 channels are currently used for our SC surveys. And we have low resolution, they are lower resolution, low frequency observations coming online in the next year or two. So while its ACT is low resolution compared to X-ray or optical instruments, it's quite high resolution compared to, for example, Planck, and it's low in noise as well. So this little animation shows you here on the right, a Planck map of the sky, and then on the left, a map where we've co-added the ACT data on top of the Planck. And so you can see the noise in the map goes down significantly, but also with the higher spatial resolution of ACT, you start to see all these small scale structures pop up. So you see these red spots. Those are actually point sources. And then remember how I said the TSC effect is a decrement at 90 and 150. Well, that little blue spot right there is a cluster. And if you get really good at looking at this, you can actually see the clusters sort of pop up. And you'll notice that they're very hard to see in Planck. So.
Yeah, I couldn't follow that, actually, that video. Where does it divide? I can't see the difference between Planck.
It might be hard on the resolution. The one on the right is Planck. Probably the easiest thing to see if you're not used to looking at CMB maps is all these red spots that are jumping out on the left side. So it's scrolling right to left. On the right is the Planck, so you can see all these red dots that pop up that you can't really see on the right. And that's essentially the increased resolution of active play. Right. So we recently put out our most recent cluster catalog, which was part of our DR5. Matt Hilton wrote that paper. It's really phenomenal. If you want to check it out, there's a link there. It's a catalog of about 4,200 SC selected clusters, all of which have optical confirmation. It's the largest homogeneous sample of SC clusters to date. And I believe pending the release of the eROSITA cluster catalog, it's the biggest largest homogeneous sample of clusters, period, although I'm not 100% sure about that. The coverage is about 1,300 square degrees, so that's all this black stuff here, and it has significant overlap with optical surveys, so DS and blue and Hypersupreme Cam. On the right here is just sort of a real space plotting of where those clusters are. So we're on Earth here in the center, and every blue dot is a cluster. And for reference, the furthest out thing here is at about Z of 1.9. Right, so how do we actually do the mass richness scaling relation? So, like I said, here's the plot I showed you before, which was sort of the state of the field 2 years ago. And so Each of these was a targeted observation. Each data point here you see is a targeted observation. So they took one of these instruments and they did a patch at the site where they thought there was a cluster, and they made an estimate of the SC effect. But if you have a large maps of the SC effect, you don't need to do that. You can do what we call forced photometry. So as part of making the cluster catalog, we have these filtered maps of the SC signal. And the map is constructed such that each pixel records the centralized Compton Y or SC value that a cluster would have if it were detected at a given location in the map. And then you can simply extract that value at the location where you think there should be a cluster, so at the location of the MaDCoWS cluster, and then you can convert it to mass. And then, so those masses are free of what's called the SC selection bias, or they don't need to be deboosted if you're familiar with that term. But they do contain other biases, which I'll get to in a second. And so this is what it looks like if you do that. So that prior plot lived basically up here on the top right, and it was a little messy by itself. And you can see that when you add all the clusters, things get even more messy. So yeah, this is what we were sorting through. On the left here, by the way, it's not converted. That's just the SC signal. So by probably the largest source of bias is infill of the SC signal. So the match filter that's applied that turns the frequency maps into SC maps doesn't know what's causing the emission that it sees. So if you have a point source that lives in the cluster or just in the field and happens to be at the same location as the cluster, then the filter cannot distinguish the emission of the cluster from the emission of the point source if the point source is appreciably emitting at 90 and 150. As I said earlier, the SC signal is a decrement at 90 and 150. So if you have emission at 90 and 150, it'll have the effect of essentially infilling the SC decrement that you observe. And so that's essentially what you're seeing on these plots on the right here. On the plot on the left is a stack at 220 gigahertz on the ACT clusters. And you see basically nothing, which is what you should see since, excuse me, as I said before, 220 is a null of the SC. And on the right, you see a signal here. That's the MaDCoWS, same idea, but stacked on the MaDCoWS position. And you see a signal. So clearly there's some there's on average some sort of emission going on in the MaDCoWS clusters. And our preliminary estimate is that this is about at the 1.1 to 2. I'll actually get back to the estimate in a bit. So remember how I said we have poor resolution? Well, we can't get those, we can't actually resolve out those point sources. So from our perspective, the perspective of ACT, we don't have the resolution to resolve a point source in a cluster. We just see, you know, one emission. However, if you have a high enough resolution instrument, like say Mustang 2, you can actually just map the cluster and actually resolve the point source and remove the emission from the point source manually. And Simon actually has a proposal in to do this. So this is the proper thing to do to remove the infill, but we sort of did the best that we could in this work. So we first looked at IR contamination. We basically used Herschel data, and we, sort of fit the emission from Herschel and 220 to a modified black body, a gray body. You can see up here. The ACT clusters did not have significant amount of emission in any of these bands, but the MaDCoWS did. So we don't report IR contamination for ACT, just for MaDCoWS. We have a best fit temperature and spectral index for this, and this all sort of agrees with literature values for the temperature and spectral index of dust in high Z clusters. And the infill effect from this, we think, is about the 1.5% level. One thing to note is we had very, very limited Herschel follow-up. We only had 33 ACT clusters with follow-up and 66 MaDCoWS. So this is not comprehensive. We would like more follow-up in order to be able to say with more certainty the level, the distribution of infill, I should say. So we might know the average reasonably well, but we don't really know about the distribution. We don't know, is there a high infill tail, or is this some sort of we don't know what the distribution looks like. For the radio, we saw significant radio contamination in both. So here, what we did was we took the radio fluxes at 1.4 gigahertz and 3 gigahertz, formed an estimate of the spectral index from that, and then propagated up to 90 and 150. Now, obviously, it's not great to propagate all the way out there, but it's not unprecedented. And unfortunately, like I said, without the spatial resolution to really resolve these point sources, you have to go to a different frequency where you don't have the SC effect and you just have the point sources left. So the results from this pin the infill at about the 2% level for ACT. But one thing to note is that this is extremely sensitive to the spectral index that you assume. And we found a broad range of spectral indices for ACT and MaDCoWS clusters. And like I said, we're propagating this spectral index all the way from 3 and 1.4 gigahertz to 90 and 150, so almost 2 decades. And so there's no guarantee at all that the spectral index will be the same. So really what you want is a targeted observations of point sources in these clusters at frequencies near the SC frequencies, so that you have a better understanding of what the spectral indices look like at those at the actual frequencies of interest. And like I said, the sort of takeaways, it's about a 1 to 2% effect, but there's a significant tail. There's about 10% that have 10% infill, for example. So if you take that into consideration, it's still kind of a mess. So what I'm showing on the right here is the best fit scaling relation in blue, and black is the MaDCoWS preliminary mass richness scaling relation. Our slope actually agrees pretty well with the preliminary slope. We have an offset to lower masses, which is perhaps not unexpected, as we included a lot more lower masses than they did. But sort of the key thing is that the intrinsic scatter we measure is absolutely enormous. It's at like nearly a 30% level or something like that. And so there's an absolutely humongous scatter between the richness and the masses. So yeah, if you want, it's probably not, it is not, that nice tight X-ray SC scatter relation. It's a lot messier than that. So looking at the future, I also work on Simon's Observatory, so I'm required to, stump for it every time I give a talk. But Simon's Observatory is the next generation CMB observatory that's coming online in currently 2022. It's composed of 1 large aperture telescopes and 3 smaller aperture telescopes. It's going to represent about an order of magnitude increase in detector count over current generation CMB experiments. So we're putting about 40,000 detectors on the sky in the LATR and 30,000 across the SATs, with the capacity to expand to more than 80,000 in the LATR. For reference, current generation experiments are about 8,000 to 9,000, depending. The LAT will primarily be concerned with the small angular scale science, including cluster detection, while the SATs will cover large angular scales, meaning basically detecting, R, the tensor scalar ratio. So like I said, the LAT will undertake a cluster survey, much like ACT. So it's going to represent about a factor of 5 increase in the cluster count, somewhere between 16 and 24,000 clusters, depending on, exactly how well we do calibrating the instrument and, how well we constrain our beam and, details like that. And we should find them out to a redshift of 3 or nearly 3, with quite good mass calibration and with excellent sky coverage. So we're gonna cover about 40% of the night sky with the SO cluster survey. And you can check out the science paper if you want some details. So just in conclusion, the cluster abundance function is a strong probe of cosmology at large scales, but in order to understand the cluster abundance function, you need to detect clusters at a wide range of masses and redshifts. And you need to understand precisely what their masses are, including debiasing those masses through the SC infill if you choose to measure the mass via the SC effect. And doing that, understanding the infill requires high resolution measurement of both point source flux densities and spectral indices near the frequencies of interest. But the future is bright as we've got both we've got next generation experiments coming online, both to do the SC surveys like Simon's Observatory and CCAT Prime, and to do the SC, understand the SC infill, including Mustang 2, which is currently on the sky, obviously, and Toltec, which should be coming online in the next year or so. And that puts me at almost exactly half an hour. So I'll stop there and open. Oh, I'm sorry if you were having trouble understanding me. It was SZ. Yeah, but I'll open the floor for questions.
All right, thank you so much, Jack. Anyone here have a question? I'd like to start us off. Okay, well, since there are no obvious takers, then my question is going to be a bit more general.
Sure.
So talking about these next generation observatory, to what extent is it expected to improve the uncertainty?
In the infill?
Yeah.
Well, the thing is, we don't really know about the infill right now. So I have these estimates of the infill, but obviously these are calibrated using the cluster, using the SZ measurements that we made, right? So we're asking, how much are we missing using the catalog that is missing the thing that we're trying to quantify how much we're missing of. So these estimates probably aren't unreasonable, but the fact of the matter is they're just estimates. And like I said, we had to extrapolate from radio frequencies, so not great. I think we're particularly excited about Toltec. Toltec's going to have really great frequency coverage from us, basically spanning, I think it's like 90 to 300 or something like that, around there. And they've got great resolution. They're on a 50-meter telescope. I think LMT is 50 meters, so they've got fantastic resolution, and they've got very, very high overlap with the ACT field. So, I think if you could go out and hit, 200-300 clusters with targeted observations, and get the actual spectral indices and the actual fluxes of these sources in the clusters, you could understand. What percentage of clusters am I missing because they've been completely obliterated by infill? What's the actual typical infill contamination? And then you can statistically you don't have to hit every cluster in your catalog, obviously, right? You can just hit a subset and then say, well, then we'll just apply the averages here. So to answer your question, currently we basically have no understanding of this. So any understanding would be an immense improvement, but.
Have any individual or smaller scale studies been performed on the measuring the fluxes?
Yeah, so that's what Simon's doing right now. I don't know if any of you guys know Simon Dicker, but he's a scientist who works here at UPenn, and he works a lot with Mustang 2. So they're doing Mustang 2 is currently undertaking No, we don't have a Toltec time right now. No, I don't even know that are they taking, sorry, I got distracted by the question in the chat. Are they taking submissions right now are they taking proposals? Anyway,
you happen to know?
Well, we get the answer to that. Anyway, Simon is currently no data. Oh, huh. Whoops. Well, we missed that call then. But so currently Simon is hitting about 200 ACT and MaDCoWS clusters with Mustang. So it's still a little tricky to get the spectral indices because Mustang's monochromatic. But you do have the spatial resolution to resolve. The Mustang has sufficient resolution to resolve sources within clusters. So I think that, and it's operating at 90, so it's actually observing the fluxes at the right frequency. So he's getting results as you So his work should be coming out with a paper soon-ish in the next month or two on this. And he's getting results that are unsurprisingly somewhat higher than ours. Like I said, you know, we're doing all of this. Like I said, we're estimating the infill using the infilled SC signals, whereas he can actually properly remove the clusters from the SC signals. So he's getting somewhat higher than us, but not like catastrophically higher. And I think that'll be the first. Oh, sorry, got it. The call didn't. Okay, got it. Yeah, I'd heard that they got super delayed. That is really unfortunate because I was excited for Toltec for a couple reasons, but sorry, I keep getting distracted. Anyway, yeah, I think that Simon's will be the first paper that I know of to sort of do this the right way. There have been other people in the past who've done estimations like ours, where you take observed SC fluxes, you take an auxiliary data set that has fluxes at a nearby or not that nearby frequency. Like I think some of the SPT people had, I think like some measurements at like 25 or 30 gigahertz, something like that, which was better than us. And they did a similar thing where they, you know, projected that out to 9150. But I think Simon will be the first person to do it sort of right by doing high resolution measurements that can resolve at the point source at the frequency of interest. So
hopefully that will give you some semblance of error.
yeah, no, hopefully.
Okay, does anyone have a question they would like to ask? You're all such a silent group today.
All right,
Well, I'm sure someone has something they want to ask, even if they're too shy to come out and say it. So,
well, my email is at the front of the talk. So if anyone has any questions, they can feel free to email me.
Yeah.
It's there, right? Yeah, it's there. So you can feel free to reach out to me.
All right. Well, if anyone would like to talk with Jack further, you can contact him through email. Otherwise, want to thank you all again for attending, and thank you, Jack, for this awesome presentation.
My pleasure.
Yep. And for those still here, next week's talk is canceled due to additional talks for the GBT at 20 celebration. So thank you all for coming, and see you again in 2 weeks.
Have a good day.
Take care, Jack.